Hello and Assalamualaikum sir. My name is Ahmad Munir, and today I'll be talking about the impact of dynamic voltage restorer on voltage sag mitigation. So first of all, let's try to understand what a voltage sag is. So by the IEE definition, voltage sag is the decrease in RMS voltage or current by a value of 0.1 per unit until 0.9 per unit of the value in a duration of 0.5 cycles to 1 minute, as you can see in the picture here. So voltage sag is the one below. Voltage swell is not really part of our thing, but you can look there as well. Okay. So when and what causes voltage sag, right? So what causes voltage sag is basically when there's a sudden change in current consumption. Let's say you're connected to another load, and the load is suddenly drawing an extreme amount of current that it usually is not consuming. So what will happen? Kirchhoff current law says that if you're taking current, that means you're taking it from somewhere, and you're taking it from my node basically. As you can see in this picture, X1 is using a lot more. In this particular example, it's a fault, but basically it's taking current from X2. Okay, so that causes the V of X2 to drop significantly and causing the sag in voltage basically. So what are the implications of voltage sag? So there are some machinery, some processes that require a very specific sinusoidal wave to function properly, and if they don't receive this perfect waveform, their processor will be interrupted or maybe stopped, right? And this will disturb their whole overall process and will cause failures in their system, and this is definitely a bad thing. Okay. So to overcome the voltage sag, the paper that was assigned to me uses a dynamic voltage restorer. Okay, so let's look at what DNV is. DNV is, so here you can see the operation of DNV. So basically, it's usually installed between the supply and the load that is sensitive that you're trying to protect. And basically, what it does, it detects the difference in sudden voltage changes, and it will inject the circuit will inject voltage that is required to compensate back the set that occurs. So basically, how it is done is there's a voltage source converter that supplies this, and it is controlled by an IGBT. The IGBT acts as a switch. So the hysteresis voltage controller will output to the IGBT according to when the voltage sag occurs. So here you can see that after the VSC supplied voltage, basically the coupling transformer will step up the low VSC voltage to the required voltage, and the passive filter will act to reject the switching harmonic components of injected voltage. So as we know, there's some harmonic components of all these switching circuits. So that's what this capacitor is for. So here are the results from the paper. So you can see that there is a waveform from the DNV and waveform without DNV. With DNV is on the right, without DNV is on the left. So you can see that portion of the waveform is compensated back. Here as well, this one is a larger portion of the signal being compensated, and here as well, right? So these are all three different types of faults that has occurred, namely single line to ground, three-phase fault, and double to line ground. Okay, so the additional method that I propose that we implement is the uninterruptible power supply. Okay, so here you can see a diagram of the uninterruptible power supply. So this is specifically the double conversion uninterruptible power supply, which to me is the best type of system because it provides basically a period of time where your load is completely protected from whatever is happening on the supply side. So basically the way it works is there's a battery in between the load and the supply. The supply AC coming from the grid is converted to DC to charge the battery, and the battery is then converted back into AC to supply to the load. So basically this battery acts as a perfect source of energy for the load for a period of time, and any irregularities that's happening on the supply side is completely mitigated. But obviously this comes with their own sets of power losses. As we know, when there are conversion losses when you're rectifying and inverting it back, and there's also battery charging losses. So, but it does provide with this good good conformity of the voltage, right? So that's the price you pay, and that's what you're getting back in return, which I feel like it's a good um, implementation in this particular application. Okay. So here you can see a bit of the more interactive picture. You can see that there's irregularities that's happening on the left side of the picture, right? The signal, and it's coming, charging the battery, and all this, converting and inverting back, and you can see a perfect sinusoidal wave is coming to the load. So this is basically what we want, right?